Hey guys, this is a quick video, hopefully, on, yeah, pretty much a whole bunch of stuff from grade 11 math. So just trying to help you out with some of the homework questions because I didn't have time to review a ton of stuff. So function notation. So if you remember, we use function notation when we're dealing with functions. So a quick little aside here. In grade 11 math, we learned what the difference between a function and a relation was. So we were able to classify things as functions or as relations. And what we determined was, let's take a graph for example. Let's do a straight line versus a circle. So what we noticed in grade 11 was we could call this straight line a function, but this circle is not a function, so it's just a relation. And the way we can tell that is for every input, so for every x value that we see here, so when x is 1, 2, 3, -1, -2, -3, any value of x in this linear graph has only one y value. And if you think of y like the answer or the output of the function, of the relation, we only want one of those with every x. So when x is 2, I can tell that the y value will be 3 perhaps. Or when x is 0, I can tell that the y value will be 1. So I can tell you with certainty what the y values will be for every x. Whereas when I look at not a function, so here I've got a circle. So let's just check out our x values here. If I was like, hey, when x equals 1, what's our y value? Okay, turns out there's not a certain answer here. There's actually two different answers. When x equals 1, y could be two different things. Same with when x equals 2. Y could be two different things. So there's not a one certain answer. So when each x value has multiple y values, they're not a function. So if x values have multiple y values or more than one, they're not functions. But when x values have only one y value, they're functions. So linear is a function. Also, parabolas are functions like we did last year because for every value of x, there's only one value of y. So we like to use this function notation to represent functions. So in the past, we would have said y equals 3x squared plus 5. But now that we know this is actually a function because it's a parabola with the squared thing tells us, we can use function notation. And function notation is this. And we pronounce it f of x. F of x is how we pronounce it. And it just helps us, well, first of all, tells us that this is a function because we're using function notation. But also it's just a more concise way to write things. So now we can use our function notation to solve for different inputs, for different values of x. So let's just say this was a parabola, and I know this parabola looks something like this. 5, it's got an x-intercept or y-intercept at 5, and then it opens up. So that's what my parabola looks like. Maybe I was curious, like I was wondering, hey, what's the y value when x is 1? So I want to know when x is equal to 1, what does y equal? So instead of having to write it like this, I can actually use function notation to ask that question. And how I do that is I would just say, what is f of 1? I want you to determine f of 1. And what this thing means here is it means that. It means when x is equal to 1, right here, what would y be equal to? Okay, my graph's drawing like really bad, so don't use these values. So to figure it out, we would just sub 1 in for x. Sub 1 into x. So if we're trying to find f of 1, x will become a 1. So f of 1 is equal to 3 times 1 squared plus 5, which is 8. So now I know that f of 1 is equal to 8. And another way of writing this is when x equals 1, y is equal to 8. Or you could say there's a point at 1 comma 8. So these three ways right here, this, and this, are all saying the same thing. X equals 1, y equals 8. F of 1, 8. So that's telling us when x equals 1, the y value is 8. So that's what function notation is. And that's how we use it. Okay, next thing. This is just a very rough review here. So I'm already 6 minutes in. I've covered like one thing. So a quick quadratics reminder. You did this in grade 10 and in grade 11. So I'm not spending too much time on this. But quadratics are of degree 2. So all of their equations, their largest exponent will be a 2. So for an example of a quadratic could be something like x squared plus 3. We know that's a quadratic because of that squared. And quadratics are all parabolas that look like this, or they could open down. So these ones would open up, and these ones open down. And we can tell what they look like according to their equation when they have a positive in front of their x squared value, they open up. And if you have a negative in front of your x squared, they open down. Even if the equation surrounding them is whatever it is, it doesn't really matter. As long as our first coefficient here is positive and this one is negative if it's opening down or up. Okay, some more stuff to tell you about quadratics would be, do you remember we did this form for quadratics? I'm like blanking on what it looks like here. X minus h squared plus k. That's like the form it looked like in grade 10, but I forgot. In grade 11 we ramped it up a lot and we added in like a k value. I think we changed that to a d plus c. Whew, crazy. So we learned this crazy equation here, and we learned about this value being a vertical stretch or compression. Vertical stretch or compression. We learned about our k value being a horizontal stretch or compression. So A could make your graph really skinny or really wide. And same with A, K. D was the horizontal translation. So that just means it moved your graph left and right. And then C was the vertical translation. And that just moved your graph up and down. So those were like transformations that we did of quadratics. So if I gave you an equation like y equals 2x minus 1 squared plus 5, you should be able to know based on like what all of those a, k, d, and c mean, what's happening to this. So here we've got a vertical stretch by 2. This x minus 1 means our graph is actually moving to the right 1 space. And then this plus 5 means it's moving up 1. So I know this one's weird, but remember the one in the brackets was always like seems backwards because our default equation had a minus in it. Okay, so anyways, if I wanted to just draw a rough sketch of that, I know parabola is normally like just a straight up x squared parabola looks like that. So if I had to do all these translations to it, Oops, just deleted mine. If I had to do all those translations, first I would find my vertex, which I know will be given to me by my left and right up and down shift. So I actually know since I'm moving right 1 and up 5, my vertex will now be at 1, 5. So over 1, up 5. This is a super rough sketch. And then it doesn't really matter like my pattern, like don't worry about the super details of that. But I know I'm going like over 1, up 2. And then it'll just be going up from there. So I can draw rough sketches. Here's another one. Say we have y equals negative 3x plus 1 squared plus 3. Let's use a different number just so we don't get confused. Plus 4. So here's a graph, or a function. So we know right away these guys give us our vertex. So our vertex, since this guy's going left 1, it would actually be a negative 1, and up 4, so that'd be a 4. So we got a vertex at negative 1, 4, so we'll just rough sketch it there. And then we know this negative 3 is telling us two things. The negative is telling us it opens down, and the 3 is just telling us we have a stretch, so our graph's going to be a bit narrower. So we have a graph that looks like that. So as long as you can kind of rough sketch these guys, and even if you added in the really annoying k value, even if you had anyway, I'm not going to do one. It's just going to affect how wide or how narrow it is. It's not a huge deal. We're not like super accurate graphing these. Sometimes we just want to be able to tell their domain and range. So let's look at this guy. For the domain and the range, if we wanted to describe it, remember the domain is just what can x be? So it's just like, what are all the possible values of x? So if we look at the x-axis here, and we look at all of the possible values of x, well, this graph goes forever. Like forever. And see how it's like slightly getting wider and wider? So eventually it's going to hit, like, it's going to go forever. So it's going to hit every possible value of x. What value of x would it ever miss? Nothing. So in this case, since the domain could be anything, we would say that x is an element of the set of real numbers, meaning that x can be any number. And then if we want to determine what the range would be of this function, the range has to do with the y values. So if we look at all the y values on the graph, well, I know my graph is going to go down forever, so I'm not guessing, I know. It's going to hit every value of y in the negative areas here. But if I look up, it looks like I max out here at 4. So that's supposed to be 4. So that's the highest. I'll never have a y value of 5, 6, 7, 8. It's never going to go up because it starts here and then it goes down. So for my range, I would say that y has to be less than or equal to 4. Because it's starting at 4 and then it's going down. So the domain and range, we need to know like a critical point on our graph, like the vertex. We need to know the direction it will open, and then that's pretty much all the information we need to gather for domain and range. So I think I also asked you to find domain and range of other functions. You just kind of have to remember what those functions look like. So we know quadratics. You should know straight lines are kind of in the form y equals mx plus b. They just have a single x. So if we had like 2x plus 1, if you recall, if it's in this form, that's our slope, and that's our y-intercept if it happens to be in this form, or you could make it in this form. So we know that we have a y-intercept at 1, and since our slope is 2, that means we could go up 2 over 1. I could also go down 2 over 1, and that's what our graph's going to look like. So if I wanted to describe the domain and range of that, well, it goes forever in both directions, so it's going to be xer, yer. Another function that we learned last year was radical functions, so like the square root of x. And all of these functions can have any transformations, so they can have an a value, it can have a k, like a stretch, minus d plus c, so they could look like that. And D and C, Those are the important ones. Those are going to tell us like if it's shifting or whatever it's doing. So if you have like an x plus 1 in there, that guy is going to be important. Or a minus 5 out here. Then we know that our graph's actually starting left 1 and down 5. So it's starting down here. And then remember your classic square root function just kind of looks like this. It's kind of like 1/2 of a parabola going sideways. So that's what it looked like. So if I had to describe the domain and range of this, well, every x value looks like it pretty much has to be bigger than -1. So I would say x is greater than or equal to -1. And then for my range, if I'm looking at the y values, I notice it's starting down here at -5, and then it's just going to keep going up. So for my range, I would say y has to be greater than or equal to -5. So you kind of want to figure out like your critical point. So in a parabola, that's the vertex. In a square root thing, that's this guy here where the graph is starting. Okay. And, oh, I should say something else about quadratics. And that was roots were a big thing last year and in grade 10. X-intercepts. We're going to be doing that again this year. So to find the roots, we liked it to be in factored form was the best. So if you're given a quadratic, no matter what form it is, you can always switch it to factored form. So if you're given a quadratic that looked like, x squared plus x plus, oh, okay, I can't make one up, 5x plus 6, say, and you want to find the roots, well, maybe you should factor it. So we know it's a simple trinomial, so I'll factor it into 2 brackets. And then to find the roots, I'm going to set y equal to 0. And then I'm going to separate my brackets and find out what x equals. So I'm going to set each bracket equal to 0. Sorry. And then I'm going to solve for x. So x equals -2 here. X equals -3 over here. So those are my 2 roots. So this here is factored form. And then from factored form, I'm able to set each bracket equal to 0 to solve for x. So now I know this graph would have x-intercepts at -2 and -3. I also know this guy is the y-intercept. 2, 3, 4, 5, 6. So that's my y-intercept. I don't know my vertex, but I know it would be right in between those guys. Somewhere down here, wherever it is. So my parabola would look like this. Could totally find the vertex because I know the vertex would be halfway in between those. So I know the x value of my vertex would be -2.5. And then to find the y value, I could just sub it into the equation again. So yeah, I think that covers a lot of stuff. So good luck.